Hello, chemistry students. Welcome to, we're going to be looking at Big Idea 4. All right, Big Idea 4. So Big Idea 4 is about rate laws and reaction rates. So the idea with that is that when a chemical reaction occurs, you actually have the chemicals are actually, let's use a different color here. The chemicals are actually bashing into one another, okay? And so if they bash into one another hard enough, then what happens is the reaction happens. So that reaction might combine these two. Let's go ahead and just add a plus here. So that reaction, if they smash into each other hard enough, they might form this new thing. So we have this idea called kinetics. And kinetics is the study of that particular idea, how the bashing together of these molecules, the actual collisions of these molecules affects the rate of reaction. And so rates of reaction are exponential. So it can either be, it can be to some power. And so what that means is that when you adjust the concentration of a reactant, it will affect the rate based off of that particular power of reactant, which we call a rate law. So a rate law looks like this. So a rate law looks like rate equals K, and K is the constant for that rate law, which is something you can calculate, times the concentration of your first reactant to whatever power it is, times the concentration of your second reactant to whatever power it reacts at. Now these powers that are the reaction orders, we call them, have to be determined experimentally. You cannot just look at a balanced equation, for example, and figure it out. You have to determine this experimentally. So let's go ahead and look at a data set and see if we can do that. So here's a little reaction between a permanganate and a chlorate ion and a hydrogen ion. And so what it does is we have an oxidation reduction reaction where the manganese is going from a +7 oxidation state to a +2. So it's gaining electrons and getting reduced, and the chlorine here is oxidizing and going and taking then, or giving the electrons to the manganese. And so we have this little setup, this little oxidation reduction reaction. So the idea is, if I change the amount of permanganate, how does that affect the speed at which this reaction goes? So then that would be like adding more of one particular reactant. Is that going to change the collisions at all? Is that going to increase the collisions? Is it not going to do anything? What's it going to do? And so here's our data. And so what we've done in our data is we've taken experiment 1, we put together 0.1 molar, 0.1 molar, 0.1 molar, and this was our rate. Our initial rate of our reaction was 5.2 times 10 to the -3 moles per second. So that's our initial rate of reaction. So a rate of reaction is going to be kind of like speed, right? Miles per hour. So this is the amount of moles of product produced, or actually it's more like the amount of moles of reactant disappeared per second. So we have 5.2 times 10 to the -3. All right, and then if you see in the second reaction, what we did is we changed the concentration of the permanganate, and that did affect the rate. And so that's how we get this data right here. We take and we measure the rate initially, and then what we do is we change the rate of one of them and see what that does to the initial rate. Okay, so let's go ahead and look at this. And so first of all, we're looking for this rate right here. We have 3 reactants, 1, 2, 3. So here's my A, right? Here's my B, and here's my C. And so this is the format that we would use. So what we want to figure out from this experimental data is these exponents right here. And all rate reactions look the same, and so your little A, B, C is dependent on how many reactants. If you have 1 reactant, well then you just have A. If you have 2, you'll have A, B, and then 3 like we have here, we have C. All right, so let's take a look at A. So first of all, A is our permanganate. So what happens between here and here? Because between experiment 1 and experiment 2, right, for A, and so let's solve for A. So A, we went from 0.1, right? And we increased that to 0.25. So that's an increase of, well, it is a 1.5 increase, right? So, or 2.5 is the increase. So this is 2.5 times bigger, right? So if you took this 0.1 and multiplied by 2.5, you would get that, right? So, we have a 2.5 increase. And so what did it do to the rate? So the rate went from 5.2 times 10 to the negative third to 3.3 times 10 to the negative second. So what we want to know is how many fold increase did we have here? And so if we divide this into this, we come up with something like 6.3. All right. Now, if I was taking 2.5, right, and putting it to the second power, I would get 6.3. So anything to the second power is, so clearly A right here is to the second power. If I would have, instead of going 2.5, if I would have gone from 0.1 to 0.2 to the second, so what I would have expected was that this would have quadrupled, but instead we went to the 2.5 increase, and so it went from, it did a 6.3 fold increase. So what we see right here is the power, this exponent right here is squared. It's 2. Okay, so our rate is going to equal our constant times, we have our permanganate, so MnO4, and that one is squared. And we know that's squared because when we took it from 0.1 to 0.25, this initial rate went up by 6.3 times. And so that's 2.5 squared, 6.3. All right, so now let's look at B. And so B is going to be right here. We have ClO3. We're going to put it right here. And what we want to determine is what is that exponent for B. All right, so let's look at B. So which one of these experiments changed B? It looks like number 3 did. So if we look at number 1, they're all 0.1, 0.1 across the board. If we compare this, I'll go ahead and erase this now. If we compare the first experiment to the third experiment, this is going to give us something to work with, because we have everything is 0.1 here, and the only thing changed from experiment 1 to experiment 3 is the concentration of ClO3. And the concentration went up 3 times. We went from 0.1, right, to 0.3. So that's a 3 times increase. And so what is my new, go ahead and erase that because that was for the other data. So what is the amount that I increased here? I got 1.6 times 10 to the second, and it went from 5.2 times 10 to the third. Well, if you divide that into that, you'll find that it's 3 times. So if I tripled it and my rate increased by 3 times, then that's just to the order of 1, right? If I triple it and it ends up tripled, I've just gone by itself. So this is a first order reaction. So the exponent here is 1. So whatever I do to this, it's going to do the exact same to the rate. And whatever I do to this, it's going to change the rate squared. So if I double it, it's going to quadruple, like 2.5. It's going to go 6-fold, or 6.3. And you might be asking, well, why did you just compare the first data with the third data? Because I want to isolate only when B changed. If I went from here to here, right, then I have 2 things changing. But when I ignore this one and I go from this experiment to this experiment, the only variable changing was B right here. All right, so now let's look at the hydrogen ion. So the hydrogen ion, if I look at the first experiment, this is 0.1, this is 0.1 from the first to the fourth. I'm going to connect these two. This is 0.1, this is 0.1, and then this one doubles. And that's what I want to do. I want to look at my data and find the 2 experiments where only the one that I'm looking for changes, and the other ones remain the same. That way I isolate the one variable. All right, so this one doubles. I go from 0.1 to 0.2. So what happens to the rate? Well, if I take 7.4 times 10 to the negative third, and I divide it into 5.2, or I divide 5.2 into 7.4 times 10 to the negative third, I find that I went up by a 1.5, right? So this to this is 1.5. So what is that? Well, how would I, if I doubled something, how would I get 1.5? Well, I could go to the 0.5 power, or the half power. So that's clearly what happened. Because if I take 2 and I go to the power of 0.5, I get well, it's not exactly 1.5. It's more like 1.41, but you can get it. And actually, that's when you divide this into this, it is more like 1.41. So we're clearly going to the 0.5 power right here. So this is 2, this is 1, and this is 0.5. And now that we know those exponents, we can take any one of these data, it doesn't matter, and we can actually solve for our rate constant. So let's go ahead and do that. Let's take this last set of data right here. So our rate is 7.4 times 10 to the negative third. And so I'm just going to look at the data from this one, because I know the orders of all of my things. So I could run each one of these experiments and throw the data in here, and I'm going to turn out the same number for my K every single time. So once you've solved this and you know the orders of every single one of your reactants, you can plug that in, and you can plug in the data from each one, and you can solve for your rate constant. All right, so my rate is 7.4 times 10 to the negative third, and that's going to equal K. K is what I'm solving for, times, in this one I had 0.1, right, and that's going to be squared, okay, because that's to the second order, times this one is also 0.1. 0.1, that's going to be to the first order, so I don't need to write any exponent there. And this last one is going to be 0.2 to the 0.5 order. Now, if I multiply all of these together, I get something like 4.47 times 10 to the negative fourth, right? And so I have K times that. So now all I'm going to do is I'm going to divide this by this to solve for K, and isolate K by itself. And it turns out that K, in this case, equals 16.5. So my rate constant for this one is 16.5. Now you could run all of these data in here with these initial rates here and everything in here, set them to the orders, and you're going to get 16.5 as the rate constant for this particular reaction in this particular situation. So if you're given a set of data like this, you can use this to figure out all of the reaction orders, and you can figure out the constant for this rate reaction. Now remember, all of this is just describing the interaction of these molecules together. And a rate, one last thing on here, this is really important. A rate constant has a different unit depending on the amount of reactants that are there. Okay, for example, rate is measured in molarity per second, right? So in this case, I had 7.4. Right, when I just did this multiplication right here, I had 7.4, so that was molarity per second, right? And so I divided that by all of these, and each one of these is molarity. So I had molarity squared, I had molarity of the first power, molarity of the 0.5 power. So essentially, that would have gone like this. So I had molarity squared times, times molarity of the first power times molarity to the 0.5 power. So my unit, and because they might ask you to solve for the unit for your K. And so what you have to do is you have to take your rate, which is right here. So this is the unit for rate, and this is the unit for each one of these that I multiplied in here, right? And you just have to essentially cancel one, because you got molarity on top, just one of them. You always have one of them, because rate is always moles over second. And so that'll take out one of them. and you have seconds on the bottom. So if I just count up what's left over, I have molarity squared to 0.5, so I have molarity to the 2.5 multiplied by seconds. So I would say this is 16.5 molarity to the 2.5 seconds. All right, now I know that seems weird, but it's really simple to figure out your units for your constant, because all you got to do is figure out, you know, how many molars do you have, or how many moles do you have when in molarity. So if you're squared and squared, that'd be 4. You know, if you here I have squared and 1, that's 3. One last thing, let's look at the overall reaction order. So we figured out that the order for permanganate was second order, the order for chlorate was first, and the order for hydrogen was 0.5. So the overall, you just count all of it up. So 2, 3, 0.5. So my overall reaction order for this is 3.5. So that's my reaction order for the overall thing. All right, well, I hope this kind of makes sense a little bit and gets you kind of thinking about that. So in the next couple of videos, I'm going to go through and we're going to sort of break up first, second order reactions and their half-lives.